Okay, let's start our live practice session for week 10. So, in last week, we have seen some basic iterative methods. In this week, uh, the week 10 lecture videos are on mostly the advanced methods for solving system of linear algebraic equations. Here, we have seen some of advanced method or some sophisticated method which can be applied when the CFD problem or the problem uh, if the problem demands or when we are facing some hurdles in the hurdles as like uh, in the convergence or due to the time taken for the convergence or such things. If we are facing some issues or there is some drawbacks with the basic methods, we can go to the advanced method. And such advanced methods have been covered in week 10 lectures like our relaxation method, ILU methods, alternative direction implicit method. All such advanced methods have been covered in week 10 lectures. So let's move on to questions. First one, first question. Which of the following properties of a coefficient matrix A in a linear system AU is equal to B guarantees the convergence of a Jacobi iterative method? So the question is on the properties of the coefficient matrix A, which will guarantee the convergence of the system when we are following an Jacobi iterative method. Options are A. Diagonal dominance, option B. Positive definiteness, option C. Symmetry, option D. Strict triangularity. So this is a basic, not an advanced question. It's something what we have discussed in the last week also. You can inbox your answers. Yes, you are right. Option A, that is diagonal dominance. From the given list of options, the best option that matches the question is diagonal dominance. Diagonal dominance of the coefficient matrix guarantees the convergence of an iterative method. Actually, when we have a sparse matrix also with diagonal matrix, diagonal also having diagonal dominance, then such matrices, if our discretized equations or the discretized equations from our CFD problem can be formed to a sparse matrix with diagonal dominance, then such matrix, such coefficient matrix will guarantee the convergence. Please trying to join it. Next question. Compared to Jacobi method, the Gauss-Seidel method achieves faster convergence. Now, suppose for a particular problem, the Jacobi method is achieving a faster convergence when compared to a Gauss-Seidel method. Then what would be the reasons? So, uh, if if the Jacobi method is converging uh, faster than a Gauss-Seidel method for a given problem? What will be the reasons? Options are first one, reduced computational cost per iteration. Option B, exploitation of information from previous iteration within the same step. Option C, guaranteed convergence for all coefficient matrices. Option D, requires less memory storage for the iterative process. So the question is, suppose for a given particular problem, while using Jacobi method, if it is uh, converging faster with respect to the Gauss-Seidel method, then what will be the reason? Options are A, reduced computational cost per iteration. Option B, exploitation of information from previous iteration within the same step. Option C, guaranteed convergence for all coefficient matrices. Option D, requires less memory storage for the iterative process. You can inbox your answers. Yes, you can. If there is a doubt, you can inbox your doubt. Yes, your answers are right. Option B, exploitation of information from the previous iteration within the same step. So, because suppose in Jacobi method, the phi of n plus 1 uh, I comma j is calculated from phi of n in all the surrounding sets. So that is, all the values will be taken from the uh, all the surrounding values will be taken from the previous iteration. While in Gauss-Seidel, uh, we will be taking the recent solution or the uh, updated solution. Suppose we are having, this is our point ij, then this is, so in Gauss-Seidel, the updated solution, that is the uh, west and south values will be, we might have been swept from those directions, already swept those directions. So these values in the n plus 1 step, or that is the current iteration, these values, that is the south and west values, will be, we will be having those values. So in Gauss-Seidel, this is for Jacobi. So, for Gauss-Seidel, y of n plus 1 is equal is calculated from phi of j is calculated in the surrounding values, surrounding neighbors, also plus phi of n plus 1 of the neighbors. So which all values have been uh, iterated or updated in the current step, we will be taking that along with the steps. Those are unknowns in the current step. That is here, the upper portion on the right side, that is the north and east values of our current cell will be unknowns in the current iteration. So that values we will be taking from the previous steps. That is, we are taking the last updated values. So this last taking this last updated values in Gauss-Seidel iteration makes it uh, more faster compared to Jacobi method. Moving on to next step. Which of the following statements about the relaxation parameter omega in our relaxation method is true for optimal convergence? The question is on our relaxation method. And also on the relaxation parameter omega. So options are omega should be close to 0 for faster convergence. Option B, omega is equal to 1 corresponds to Gauss-Seidel method. Option C, the optimal value of omega depends on the properties of Gaussian matrix. Option D, a higher omega value always leads to faster convergence. You can inbox your answers. The answer is option C. The optimal value of omega depends on the properties of Gaussian matrix A. In successive or relaxation method, the omega uh, uh, depends on the Gaussian matrix. Next question. Preconditioning is a technique often employed with iterative solvers in CFD. So we have discussed what is preconditioning in the last 2 weeks lectures. So the question is on preconditioning. So preconditioning is a technique often employed with iterative solvers in CFD to, option A, reduce the overall number of iterations required for convergence. Option B, transform the system of equation into diagonal form. Option C, guarantee convergence for any iterative method. Option D, improve the accuracy of the solution at each iteration step. So the question is about requirement or the need for a preconditioning. We know we do different preconditioning for different methods, but what is the ultimate aim uh, for using a preconditioning uh, before we start iterating the uh, system of equations? You can inbox your answers. Okay. Uh, Actually, in the interactive section, I'm this is the answer to your questions, Mr. Mayank Pandey. Actually, we are not discussing the question of the assignment as such. We are only helping. We are only giving you additional content that will be in uh, that is related to the one particular week's lecture. This is for week 10's lecture, 10th week lectures. That is in 10th week lectures. The course content is on advanced uh, methods for solving the system of equations. So that we are discussing. Actually, this is some additional content for you to learn. Not we are not we are not allowed to discuss the assignment questions in the TA sessions. In the interactive session, what we are doing is to uh, yes, I know, but if you have following the course thoroughly, then you can easily pass the exam. That is not a big deal. And if you are finding the course uh, much difficult, even if you skip some of the advanced topic, because in this particular course, some 2 to 3 week are on very advanced topics. So if you are finding it difficult, you can skip that content, and even if you study the basic form, that is even if you study or was around 9 week of lectures, you can easily pass the exam with very good grade. It is not that difficult. uh, it's not like memorizing things. It's the course is about to CFD is a process of understanding the method. So you can't expect the same questions to be asked on the exams. But if you understand the concepts well, you can answer any questions, because this CFD is mainly a set of tools and techniques to solve some system of equations, convert some physical problem to mathematical equations, and to solve those system of equations. So everything is very basic things. It is the concepts. If you can grasp the concepts, then you can answer any all eh, whichever questions that will be there on exams. I would rather recommend you to understand the concepts than to memorize the questions. Thank you. Moving on to our question. Um, Preconditioning step. Preconditioning is a method, is a group of techniques that is employed to reduce the overall number of iteration required. So preconditioning may not improve the accuracy, may or may not. It is not the aim of preconditioning to improve the accuracy. uh, the our what ultimate need or our main objective while establishing a preconditioning technique is to reduce the overall number of iterations. Some preconditioning techniques transform the system of equation into diagonal forms, but this question is on general question on preconditioning methods. So this is one preconditioning method, that is to transfer into diagonal form, but our main objective is to reduce the number of iteration for the convergence. And also, even though while reducing the number of iterations, the preconditioning, any of the preconditioning techniques do not guarantee any accurate solutions. So you can also can't say that while doing some preconditioning techniques, our accuracy will be very high. So our main objective is to reduce the overall number of iterations, thereby reduce the computational cost. Moving on to next question. Which of the following statements is not true about the convergence of the Jacobi iterative method in CFD? So the question is to find a false statement regarding Jacobi iterative method used in CFD. Option A, it converges for diagonally dominant coefficient matrices. Option B, its convergence rate can be slow, especially for problems with strong coupling between variables. Option C, it is easy to implement and parallelize. Option D, it always converges for any system of linear equations arising from CFD discretization. You can inbox your answers. So checking the options. Option A says it convergence for diagonally dominant coefficient matrix. Actually, this first option is a requirement for Jacobi method or iterative method, that it should be diagonally dominant. And second one, the convergence rate can be slow, especially when the problems with strong coupling between the variables. Yes, when the coupling between the variables is strong, then while using Jacobi method and all, the convergence rate can be slow, because uh, for iterative solving, as stronger the coupling between the variables, the convergence rate can be affected, and we have to move in very slow steps. Uh, Also, again, Jacobi method is easy to implement and parallelize, because all the values we are taking from the previous iteration step. In the update equation, as I have discussed earlier, all the values we are using to find out the current value of the parameter is from the previous step. So it is comparatively much easier to implement and parallelize. The fourth fourth option is our answer. That is a false statement. It says that it always converges for any system of linear equations. So it there is no iterative method that is like it that guarantees convergence. So all convergence does not depend only on the iterative method. So we can say choosing Jacobi method, the system of solutions will converge to solution. So our answer is option D. Moving on to next question. This question is again on successive overlapping method. Which property of the Gaussian matrix is essential for the convergence of successive overlapping matrix? Overlapping method. So options are option A, strict diagonal dominance. Option B, positive definiteness. Option C, diagonal dominance with a relaxation factor of omega is equal to 1. Option D, a specific sparsity pattern. You can inbox your answers. The question is on essential property of the Gaussian matrix, which will be needed for the convergence of successive overlapping method. Options are option A, strict diagonal dominance. Option B, positive definiteness. Option C, diagonal dominance. Option D, specific sparsity pattern. Yes, you are right. Option A strict diagonal dominance is what is a requirement for the convergence. Moving on to next question. When analyzing the convergence of an iterative method in CFD, which factor is most likely to have the greatest impact on the number of iterations required to reach a desired accuracy? The question is a lengthy one. In simple words, the greatest, the factor which is having greatest impact on the number of iterations to reach a desired accuracy. Options are the choice of turbulence model. Option B, the boundary condition type. Option C, the mesh size and the discretization scheme. Option D, the physical properties of the fluid. The question is a broad question on the CFD methods. You can try to answer. You can inbox your answers. Yes, you are right. Option C is our answer. The mesh size and the discretization scheme. So, while checking the other options, the choice of turbulence model only uh, required in turbulent flows, and also the choice of turbulence models uh, doesn't have the greatest impact. Also, boundary condition will vary with uh, problem to problem, and again, physical properties of fluid. These two are not having much impact on our number of iteration needed. The number of iteration will be directly proportional or directly proportional to the mesh size and the discretization used. So as the mesh size increases, we will be having as the number of nodes increases, we will have to solve uh, our set of equations at every node, which will increase the number of iterations. Also, the discretization scheme denotes uh, still denote number of nodes. The discretization scheme will choose a number of variables to be solved at each iteration. So these two uh, decide the convergence and number of iterations. Moving on to the next question. Which of the following statement is not true about the convergence of Jacobi iterative method? Option A, it converges for diagonally dominant matrices. Option B, its convergence rate is generally slower than Gauss-Seidel method. Option C, it updates all solution variables simultaneously in each iteration. Option D, the convergence rate depends on the spectral radius of the iteration matrix. So again, the question is to find a false statement regarding the convergence of Jacobi iterative method. You can endorse your answers. Uh, Actually, it's Jacobi methods uh, convergence rate is generally slower with respect to Gauss-Seidel because all the uh, values we are taking from the previous iteration step. So this is mostly true statement, but depends on the problem. It can vary, but still uh, it is most of the problems it will be slower compared to Gauss-Seidel method. So it's a true statement. And again, option A, it convergence for diagonally dominant matrix. That is also a true statement. This is also a true statement. And the option 3, it updates all solution variables simultaneously in each iteration. So that's a wrong statement because not just Jacobi, Any iteration methods not won't update all variables simultaneously. It will be updating one variable at a time. So option C is our answer. It not just for Jacobi method, but Gauss-Seidel also. We will be updating one variable at a time. Uh, One particular point we will be updating at a time. So it won't be updating all the points simultaneously in one iteration. Moving on to next question. In successive or relaxation method, it is a modification of the Gauss-Seidel method that aims to achieve which of the following? Option A, faster convergence rate. Option B, improved stability. Option C, reduced computational cost. Option D, all of the above. So the question is on the advantages of successive or relaxation method over Gauss-Seidel method. You can inbox your answers. No, it's not option B. Uh, Successive or relaxation method is aims at achieving faster convergence rate. So if you have gone through successive or relaxation method, we are uh, adding relaxation in a successive manner. We are adding relaxation in the iteration, so which will only give faster convergence rate. Again, this D option D can be eliminated if you check this option of improved stability, because stability is a property of a or stability is based on mostly on schemes, not on iteration methods. So this is not directly linked. For the stability criteria is entirely different from our iterative solving. So improved stability is not a property or something that directly relating to our iterative methods. So option B you can eliminate. Again, uh, while giving successive or relaxation, it may or may not reduce the computational cost. That this is ambiguous in statement for our relaxation. That will depend on the relaxation factor actually. So one thing what the SOR or successive or relaxation method aims when with comparison to Gauss-Seidel is a faster convergence. So our answer is option A. Next question. The convergence rate of an iterative method in CFD is primarily influenced by. Options are the discretization scheme used. Option B, the properties of the coefficient matrix arising from the discretized equations. Option C, the absolute value of residuals at each iteration. Option D, the specific turbulence model employed in the simulation. So this question will be easily answerable. you are able to find the difference between the previous question and this one. So the question here is about the convergence rate. The convergence rate of an iterative method depends mainly on which of the following. Is it on the discrete extension method, properties of Gaussian matrix, absolute value of residuals, or turbulence model employed? The question was on convergence rate of an iterative method. So whichever discretization scheme used, it will boil down the uh, partial differential equation to a system of linear equations, which can be written in the form of which can be written in a matrix form, and the coefficient matrix in Ax is equal to B. This coefficient matrix is what have most bearing on the convergence rate. So even though discretization scheme they use, suppose we have used some discretization scheme, and that particular discretization scheme is not resulting in very good coefficient matrix, we can apply some preconditioning methods to make it a better one. So the convergence rate mainly depends on the properties of the coefficient matrix that is arise from the discretized equations. So the turbulence model mainly uh, helps in simplifying the partial PDEs, while discretization scheme will be converting those PDEs into uh, linear system of equations, and such linear system of equations uh, can be written in the form of a matrix form, and the when we are writing that equation in the matrix form, that is why to solve we need some particular we have already discussed how the Gaussian matrix will be, or which schemes can be used if uh, our Gaussian is having some properties. So the convergence, so that is what I have discussed in the last question. So discretization schemes mostly linked to stability, directly linked to stability. It is not directly having influencing on convergence, while our Gaussian matrix and matrix properties will be having most bearing on convergence of the solution. Next question. When monitoring the convergence of an iterative CFD solver, a common approach is to track which of the following? Option A, the absolute values of individual solution variables. Option B, maximum change in solution variables between iterations. Option C, the norm of the residual vector at each iteration. Option D, all of the above. So the question is basically, how can we monitor the convergence of an iterative CFD solver? Options are absolute values of individual solution variables. Option B, by checking the maximum change in solution variables between iterations. Option C, the norm of the residual vector at each iteration, or all of the above. That's a simple question. You can inbox your answers. Yes, you are right. Option C, that is, by checking the norm of the residual vector, uh, we can find, we can monitor the convergence of the iterative solver. So by mostly what we have, if you have, even though if you have used CFD in any software itself, you can, it will show some plots or something that is representing the values of residual. So the residual should uh, reduce consecutively, and it should come below some set value. We will be having some tolerance limit set for the residuals. So whenever that residual norm of the residual vector goes below that particular set limit, then that's what we say a converged solution. So option C is our answer. Next question. The ADI method is classified as an, so alternating direction implicit method is which of the following method? Option A, explicit time marking scheme. Option B, implicit time marking scheme. Option C, operator splitting method. Option D, direct solver for steady state problems. So the question is on ADI, alternating direction implicit method. Which of, in which of the following scheme it can be classified under? Option A, explicit time marking scheme. Option B, implicit time marking scheme. Option C, operator splitting method. Option D, direct solver for steady state problems. You can inbox your answers. No, it's not implicit time marking scheme. It's a variation. It's mostly not. It's mostly comes under option C, operative splitting method. So in ADI, it will be splitting the time derivative term into two, and uh, splitting the time in half, mostly into half, and it will be For the first section, it will be going in one direction, and second half it will be moving in the second direction. So that's why it's called alternating directing implicit. So the time derivative term is split into two spatial directions. So it will be uh, one particular time step will be split into two, and each half will be uh, taking one direction each. So it comes under option C, operator splitting method. Moving on to next question. Compared to explicit methods, the primary advantage of ADI is, options are: option A, lower computational cost per iteration; option B, increased stability for larger time steps; option C, guaranteed convergence for all CFD problems; option D, improved accuracy for unsteady simulations. So the question is on the primary advantage of ADI over explicit methods. Yeah, checking the options. Again, we can easily eliminate option C, that it says guaranteed convergence for all CFD problems. I already said that such guarantee cannot be given for iterative methods. Again, question: improved accuracy for unsteady simulation. This is also not true. Uh, and option A, lower computational cost per iteration. We have already seen that in ADI, it is splitting the step and moving into both directions. So that will only increase the computational cost. So the answer is increased stability for larger time steps. So the ADI is an implicit scheme which will the alternative direction in the ADI will help in getting increased stability for larger time steps, or increase the you can say convergence for larger time steps. Next question: the convergence rate of ADI method depends on which of the following? Option A, choice of the relaxation parameter; option B, number of spatial directions discretized; option C, ordering of implicit direction updates; option D, properties of coefficient matrix. The question is on convergence rate of ADI. Which of the following will be mostly influencing the convergence rate of ADI? You can inbox your answers. Yes, you are right. Solution is option B, number of spatial directions discretized. So, as uh, in ADI, the idea is to split the time step and to alternate the directions. So, as the number of directions increases, uh, the chance of error propagation uh, increases in ADI. So, the important factor which will be affecting the convergence of the ADI scheme, ADI method, is the number of spatial directions in which the system is discretized. Next question. Comparing to fully implicit method, ADI typically requires which of the following? So the next question is a comparison between fully implicit method and ADI. Options are: option A, high computational cost per iteration; option B, less memory storage for solution variables; option C, more complex implementation; option D, similar convergence behavior. The question is to compare fully implicit method and ADI. Our answer is option C, a more complex implementation. Uh, Actually, if we are taking one iteration as one single direction, then the computational cost will be less compared to fully implicit scheme. Because in fully implicit scheme, we are taking all the number of variables from the current step will be more. In ADI, it will be reduced. So option A, actually it's less computational cost per iteration. But option B is also true because it will require less memory storage for solution variables compared to implicit method. But more apt answer is option C. It requires more complex implementation. Option D is not true. Moving on to next question. Which of the following factors can impact the stability of ADI method? Options are: the choice of time step size; option B, properties of the option matrix; option C, ordering of implicit direction updates; option D, all of the above. Question is, which of the following factors can impact the stability of ADI method? choice of time step uh, is in fact in turn uh, it can impact not just ADA, any transient problem. The choice of time step can impact the stability. But again, for this ADA, if you see the system, it is not for the choice of time step is not just for ADA, but all other transient problems. The choice of time step can impact on the stability because it is directly coming from the discussion scheme itself. But for ADI, if you see the ordering of implicit direction updates, so we have to decide the direction of sweep, direction of selection of movement. So we are splitting the time step and sweeping in one particular direction at a time. So that ordering of that directional sweep, direction selection can impact much on ADI. So these two options are true. And again, properties of coefficient matrix is having impact. It is not important for directly on stability, but the coefficient matrix has impact on stability. So question is a broad question asking which can impact the stability. So all the three can impact the stability, mainly A and C. B is more related to the convergence, but still it can impact on the stability. So the answer is option D, all the above. So this option B can be what I have explained earlier. You can be get confused with option B, but still option A and C are having direct relation with the question. So our answer is option D. Next question. Preconditioning can be used with the ADA method too. Which of the following? So the question is on the application of preconditioning in ADI may be required to which of the following? Option A, improve the accuracy of the solution at each iteration. Option B, guarantee the convergence of any problem setup. Option C, reduce the number of iterations required for the convergence. Option D, simplify the implementation of boundary conditions. It's again a simple question. Question is on why precondition or what's the need of preconditioning when it is used with ADI method. Yes, you are right. Answer is option C. Reduce the number of iterations required for convergence. So as I have told earlier, preconditioning with any method, our primary requirement is to reduce the number of iterations. And as we know, uh, the preconditioning any of the preconditioning methods does not guarantee the convergence. Also, improving accuracy is applicable to some preconditioning method, but it is not a general character. Again, simplifying the implementation of boundary condition is again not related to preconditioning. So our answer is option C, reduce the number of iterations required for the convergence. Next question is, ILU stands for which of the following? I mean, in the context of CFD, what is ILU stands for? Option A, incomplete lower upper factorization. Option B, implicit linearization and update. Option C, interactive LU decomposition. Sorry, iterative LU decomposition. Option D, improved large scale unsteady solver. What is the ILU in CFD? Yes, you are right. Option A, incomplete lower upper factorization. Actually, it stands for incomplete LU decomposition method. So here it is renamed as factorization to confuse, and again something like iterative LU decomposition is given again to confuse. So actually it stands for incomplete LU lower upper factorization. So here the factorization having the same meaning of decomposition. Next question. The ILU method is a type of which of the following? Options are explicit time discretization scheme. Option B, direct linear solver for sparse system of equations. Option C, preconditioning technique for iterative solvers. Option D, multigrid solver for accelerating convergence. You can inbox your answers. Question is on what is the major category in which incomplete LU decomposition method mostly fit in. Yes, you are right. It's a preconditioning technique for iterative solvers. Here, like LU decomposition, incomplete LU decomposition is also a preconditioning technique for iterative solvers. Moving on to next question. Which of the following factors can potentially limit the effectiveness of ILU preconditioning? So the question is on the limiting factor of effectiveness of ILU. Options are use of a low order spatial discretization scheme. Option B, selection of an appropriate time discretization scheme. Option C, highly ill-conditioned coefficient matrix arising in the CFD problem. Option D, implementation on a highly parallel computing architecture. Question is on which factors can potentially limit the effectiveness of ILU preconditioning. So, which of the following parameters or which of the following things can limit the applicability of or the effectiveness of ILU preconditioning? Is it the use of a lower order spatial discretization scheme? Option B, selection of an appropriate time discretization scheme. Option C, highly ill-conditioned coefficient matrix arising from CFD problems. Option D, implementation on a highly parallel computing architecture. Can you inbox your answers? Yes, you are right. Option C, highly ill-conditioned coefficient matrices arising from CFD problem. So, ill-conditioned coefficient matrix of there is something called condition number for coefficient matrices, which is something like the eigenvalue. So, eigenvalue of n plus 1 by eigenvalue of n mod of. So this the eigenvalue vector of n plus 1 and nth iteration uh, should not be abruptly, this ratio should not be abruptly large. So if this ratio goes abruptly large, then it is called a ill-conditioned coefficient matrix. So that is the ability of that coefficient matrix to handle errors. So even if some small perturbations or errors are creeping in while iterations, how strong the matrix is to fend off the effect of errors. So that is what is understood from condition matrices. I mean, ill-conditioned coefficient matrices. So in actually what is happening is for system, Ax is equal to B, this A is written as L into U in LU decomposition method. But here, this system, this L and U is more sparse, or L and U will be having less number of uh, diagonals with respect to A in incomplete LU decomposition. So this, if this system can be solved with M of phi n plus 1 is equal to n of phi n plus b, then this here, it is mostly like LU is equal to M, where if A is having, mostly A will be having 5 diagonals, this L and U will be having 3 diagonals each, and yes, M will be having 7 diagonals. So this reduction in, and again this M is split into N. So this kind of splitting to reduce the number of terms is what is happening in incomplete LU decomposition. So while splitting, this kind of splitting may not be possible when we are handling with ill-conditioned coefficient matrices. Next question. Compared to a full LU decomposition, the main advantage of ILU in CFD is. So full LU decomposition versus incomplete LU decomposition is the question. Options are: option A, higher accuracy in solving system of equations. Option B, significantly lower memory requirements for larger problems. Option C, ability to handle nonlinear terms in the governing equations. Option D, guaranteed convergence for all iterative solvers. You can inbox your answers. You can simply eliminate some of the options from the discussions we had in our previous questions. Yes, you are right. Option B, that is significantly lower memory requirement for larger problems. If you see the options, you can simply eliminate this option D, guaranteed convergence, and option C, ability to handle non-linear terms in governing equation. That is should be done in decompositions, I mean discretization steps. So it is not in happening in LU decomposition. So C and D can be easily eliminated. Then only the question is between A and B. So again, if you remembering, in incomplete LU decomposition, we are not completely decomposing into with all the elements, but with a lesser number of elements. That's what we are calling it. That's why we are calling it as incomplete LU decomposition. So the in full LU decomposition method, the non-zero entities, the number of non-zero entities will be more with respect to incomplete LU decomposition. So in incomplete LU decomposition, the memory storage required for storing these non-zero entities will be less. Moving on to next question. The level of fill-in during the ILU factorization refers to which of the following? The number of additional non-zero elements introduced into the factors. Option B, the reduction in the number of iterations needed for an iterative solver. Option C, the error introduced due to incomplete factorization. Option D, the computational cost associated with the factorization process. The question is on a particular term called fill in during the ILU factorization. So if you can think fill in as suppose we have matrices, two matrices, and we are guessing or filling some elements into it. So in that context, you can take the fill in ILE factorization. So we are having two matrices L and U. So if you are thinking in terms of that we are filling some terms, random terms into this L and U, then easily we can relate this fill in is something regarding the number of elements. So from the set of options, only one option relates to number of elements. So that is option A, the number of additional non-zero elements introduced into the factors. I already told you that A will be having 5 diagonals, where if A is having 5 diagonals, then L and U will be having 3 diagonals each. So this some of these extra terms, that is one diagonal means not one element, a series of elements. So the additional terms that is introduced in L and U is what we are saying about what we are calling the fill-in, the level of fill-in, or the amount of additional terms that is being introduced. Moving on to next question. How does ILU improve the convergence of iterative solvers in CFD? The question is on how ILU improves the convergence in iterative solvers. Options are: it directly solves for pressure and velocity simultaneously. Option B, it transforms the system of equations into a diagonal form. Option C, it clusters the eigenvalues of the coefficient matrix for faster convergence. Option D, it reduces the overall number of equations to be solved. So the question is on the mechanism of ILU, which will be helping in the convergence of iterative solvers. No, it's not option B. Uh, it's option C. It clusters the eigenvalues of the Gaussian matrix for faster convergence. Uh, we have already discussed this in the yield conditionedness. So what is happening in a ILU is that uh, these both these matrices are one is upper triangular and one is a lower triangle matrix. Here, the elements will be chosen or selected or arranged in such a manner that the eigenvalues uh, will be what reaching below some thresholds or some particular values of spectral radius and all, which will help in the convergence. Actually, what we are doing by varying the elements or converging into incomplete upper and lower matrices is that we are uh, intentionally fiddling with the eigenvalues of those matrices. So you may be remembering from our previous discussions that eigenvalues of the matrices has a direct impact on the convergence of the solution. So this is what happening in ILU. Next question. Which of the following factors can influence the effectiveness of ILU as a preconditioner? So the factors which can affect preconditioning of ILU. That's the question. Options are the type of spatial discretization scheme used in CFD. Option B, the specific turbulence model employed in the simulation. Option C, the boundary conditions applied to the flow domain. Option D, all of the above. The question is on the factors which can influence or affect the preconditioning using ILU. Yes, the answer is option D, all of the above. Because ILU is we are discretizing A into L and U in an incomplete form, where our coefficient matrix A is influenced by the discretization scheme. Here, on even if it is only just telling about spatial discretization, spatial as well as temporal discretization will be affecting our coefficient matrix A, which in turn will be affected by our use of turbulence model and boundary conditions. So, in a hierarchical model, it will be uh, influencing the effectiveness of ILU. So, it's a broad question. Our option is option D, all of the above. Moving on to next question. In the multi-grid method, the CFD primarily addresses the challenge of. The question is on multi-grid methods. In multi-grid method, The method addresses which of the following? Option A, non-linearity in the governing equations. Option B, slow convergence of iterative solvers for low wavelength errors. Option C, high computational cost for direct solvers for large systems. Option D, difficulty in handling complex geometries. So the question is on multi-grid method of CFD. Yes, our answer is option B, slow convergence of iterative solvers for low wavelength errors. In multi-grid method, what we use is we will be having different set of meshes. So we will be having different set of meshes where we will be switching to and fro in this set of meshes to get a better convergence. Moving on to next question. In a multi-grid cycle, the process of transferring the error from a fine grid to a coarser grid is called. So I mentioned that in multi-grid system there will be different set of grids. So the question is the process of transferring an error from a fine grid to a coarser grid is called which of the following? Option A, relaxation. Option B, restriction. Option C, prolongation. Option D, smoothing. So in multi-grid cycle, we have different times to transferring between, to switching uh, iterations between finder and causal grid. So in this particular question, the question is if the process is transferring an error from a finer grid to a coarser grid. So that is, we have found there is an error in a finer grid, and we are moving it, switching it to a lower or coarser grid. Then what will be the name of such a process? Our answer is B, that is restriction. That is, we can it is somewhat intuitive that uh, we have found an error. There's an error in a final grid, so uh, we don't want that error to propagate in the final grid. So what we are doing, we are uh, stopping or cutting that error there, and we are bringing it down to a coarser grid to reduce the error. So that means we are restricting the error to propagate. So that's why it's called a restriction. Option B, restriction. So as the grid becomes coarser, we can handle large scale errors in much more efficient way. Next question. It is opposite of what you have uh, discussed in the previous question. The operation of transferring the correction from a coarse grid solution back to the fine grid. So in the previous question, the question was to uh, uh, transferring error from a finer grid to coarser grid, and now we have uh, solved or corrected that particular error, and we want to switch or put this finer solution from the coarser grid to a finer grid. Then what is that process will be known as? Option A, interpolation. Option B, extrapolation. Option C, prolongation. Option D, downsampling. So in the previous question, what we don't want was we don't wanted the error in the finer grid to propagate. So what we did was we restricted, or restriction was the name. So here what we have did was we brought down that error to a coarser grid, solved it there, and we are switching it back to a finer grid. So these two terms we can simply uh, uh, eliminate, because interpolation, when we have a set of values, we will be having a set of values. Uh, so and we want to find some value in between, then such a procedure is known as interpolation. And extrapolation is to find some value beyond the range while finding the uh, uh, by finding the trend of these variables. So these two we can simply eliminate. And also downsampling, let it be there. But the thing is, what we have found is a solution, and we want that solution to propagate. So option C is the word used for that thing, that is prolongation. We want to prolong or propagate the solution from the solution we have found using coarser grid to be propagated in the finer grid. So this is a pair, that is restriction prolongation. This restriction prolongation is the pair of activities what is mainly done between the grids of the multi-grid system. Next question. Which of the following statement about smoothing in the multi-grid method is incorrect? The next question is on something called smoothing in the multi-grid method, and we want to find an incorrect statement from the given set of statement. Option A, It aims to reduce the high frequency errors on the current grid. Option B, it often involves a few iterations of relaxation methods. Option C, it directly solves for the exact solution on the current grid. Option D, it prepares the fine grid solution for the application of the coarse grid correction. You can try to answer the question by thinking on smoothing. Yes, you are right. The option is option C. The question is for false statement. Uh, that is, it directly solves for the exact solution on the current grid. Actually, what smoothing is to prepare the fine grid solution or the to prepare the coarse grid to accept the to prepare the fine grid to accept the coarse grid solution. That is the main purpose of smoothing. That's when uh, we have we found an error in the final grid and we downgraded that to a coarser grid, and then when we are switching the solution from coarser grid to finer grid, the finer grid should be this solution must fit the finer grid or that discretization. So we need to apply some smoothing, some manipulation should be done there to accept the solution from a coarser grid to be workable in a finer grid. So such a process is known as smoothing. Next question. When should you consider using the multi-grid method in CFD simulation? So basically the question is on application of multi-grid method in CFD simulation. Options are option A, when dealing with a highly nonlinear governing equation. Option B, when the computational domain has a simple geometry. Option C, when the governing equations involve multiple scales of phenomena. Option D, when memory constraints are primary concern. even though the question you can easily eliminate some of the options. Please inbox the answer. We can simply eliminate some of the options here. So when memory constraints option, if you look the option D, when memory constraints are primary concern. So uh, we already discussed that in multi-grid there are different sets of grids. So if the memory is we have some memory constraints, then we can't go for multi-grid method. So this is not the situation to choose a multi-grid method. And also option B, when the computational domain has simple geometry. So when the computational domain itself has a simple geometry, we don't have to go for multi-grid method for such advanced method. So again, option B can be eliminated. And also option uh, A, when we are dealing with highly non-linear governing equations. So when the set of equations are highly non-linear, switching establishing it between the grids itself become challenging. So here uh, this become difficult to move with. So our option is option C. Answer is option C, when the governing equations involve multiple scales of a phenomenon. So when we are having different uh, 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 geometric scales or time scales, the multi-grid method will be much suited for that particular problem, because we can choose to solve uh, according to the scales. We can choose grids according to the scales for that particular problem or particular domain. So option C is our solution. Moving on to next question. A multi-grid cycle can be classified as. So moving to and fro between grids is what we are essentially calling it as a cyclic. When it is not a cyclic manner, it is moving up between the grids. So a multi-grid cycle can be classified as option A V cycle or W cycle based on the number of coarse grids used. Option B, according to the turbulence model used. Option C, dependent on the type of smoother or smoothing employed. Option D, always a V cycle for optimal performance. You can inbox your answers. Yes, the answer is option A V cycle and W cycle based on the number of course grid used. So it can be either a V cycle or W cycle. It's not that we won't be sticking on to V cycle alone. So that is all for this week's interactive session. Thank you for joining.